So we have a couple more of these functions that we're going to be graphing. And this one, as you can see, is an example that has a rational exponent. And so we've talked a bit about these already. Now we're going to kind of put it all together here in this graph. But the domain, it doesn't necessarily have to be all real numbers, especially if you have like a square root or a fourth root, something like that. But when you have the third root, the cube root, it does allow for anything, any number to be put in and cubed and then squared. And then the first piece is just 2x. So we do have a domain of all real numbers here in this example. When we think about intercepts, we are going to think about, I guess typically I do y-intercept first. So y-intercept, if we plug in x being 0, we get y equals 0, so 0, 0. In terms of the x-intercept or septs, depending, we want to set it equal to 0, set the function equal to 0. And the way to do anything like this is to factor out the variable of lowest degree. So we have a degree of 1 and we have a degree of 2/3. So I'm going to factor out x to the 2/3. That's going to, and this is true for any kind of factoring, you'd only be able to take out the lowest degree. So I'll have 2x to the 1/3. Notice that when I multiply those together, I add the exponents and I get 1. And then that pulls from the second piece and I get this. And then that is going to tell me that x to the 2/3 equals 0, but I'm not really surprised to know that, and that tells me that x equals 0, and that's the y-intercept, so I'm not surprised. The other piece here, when I let that equal to 0, I'll get x to the 1/3 equals 3/2, and then I'm going to cube both sides. So that's the key thing to see there, is you have to cube it, and I get x equals 27/8. So that's a little over 3 and something. So I'm going to have the 0, 0 again, and then 27/8/0. So if I want, I can put both of those. You can put those on your graph that you have, those 2 points. When we think about symmetry, if we were to plug in a negative x to something like this, we're going to have a negative x here. We're going to have a negative x here. For this, that's going to be negative. The second piece here, if you take negative x and you take the cube root, that's still going to be negative, and then you square it, that's going to be positive. So you're ending up with the same thing there. However, when you look at that, you can see that, the first piece is different and the second piece is the same. So of course that doesn't mean anything for the whole piece overall. So whatever. So the point is, it doesn't have any symmetry. So I'll just put the word none. In terms of asymptotes, you can see that with the domain of all real numbers, you would not have any vertical asymptotes. Horizontal asymptotes are only going to come when we're thinking about limits as we go to infinity, and as that happens, these values aren't going to approach anything. So we don't have any asymptotes on this either. So, we don't have a lot of information right now, and really it's not going to be until we take a derivative that we get anything exciting. So when we take the first derivative, and you can obviously pause if you want. So we get a pretty basic derivative here, but we do want to be careful, and this is where students have a tendency to kind of mess up, quote unquote, because they set it equal to 0 and they bring the 2 to the other side and they divide, and then they cube and things like that. But when you think about this, really the best thing to do is realize that you have a fraction here, and that there is a place within this fraction where you can't have a denominator that's 0. So what I would do is I would I would give both of these that common denominator of x to the 1/3. The first one has it, the second one doesn't. So that's going to give me this over x to the 1/3. You notice if I divide it, I'll come back to what I started with. And then what I'm going to do is I set it equal to 0. 2x to the 1/3 minus 2 over x to the 1/3. So I do care, of course, about when x is 0. That's really important. That is where the derivative is undefined. And I also care about when the derivative is equal to 0 in the terms of the numerator. So that's going to give me basically 2 equals 2x to the 1/3, or x to the 1/3 equals 1. So of course that implies that x equals 1. So x equals 1 is an important point. And so now I'm going to make my sign chart, and I'm going to put on x equals 0, and then I'm going to put on x equals 1, and then I'm going to check. So on, and I'm putting this into the derivative, so I can put it into any of the derivatives that I found, any version, whatever works for me. I'll probably put it into this one. That'll probably be the most helpful. So if I put in a negative number, let's say something like -8, for example, when I take the cube root, I'm going to get -2. And when I put that into the derivative, so I'll have 2 times -2 minus 2, so that's negative. And in my denominator, -8 to cube root of that is -2. So I have negative over negative, so that tells me that we have a positive. So our function's increasing up to 0. We do want to make a note here that our derivative is undefined at 0, so that matters, but notice it is 0 is a perfectly fine function to put in the original. Now if I put in something like a half, all I really care about is the fact that 2 times a half to the cube is, the cube root of 1/2 is a small number. So that's going to give me something less than 2 when I multiply it by 2, and so when I subtract 2 from that, it's going to be negative. And then when I divide that by some positive number of the 1/3, that's still positive. So I'm going to be decreasing from 0 to 1. And then when I put in something greater than 1, something like 8, I'm going to have positive on the top and positive on the bottom, so that's going to give me positive. So the function is increasing and then decreasing and then increasing. And if we put in x equals 0, because we can put in x equals 0, we do get a y value. So it's not an asymptote, it's just that the derivative is undefined. It's a vertical asymptote in terms of the derivative, but it's a continuous function. So notice the difference there. So at 0, 0, we actually have a local max, and then when we put in x being 1 back into our original, y is going to equal, looks like 2 minus 3, and that'll give us a -1. So we have 1, -1, and so that's going to be a local min. Okay, and so now, because increasing and decreasing, now we think about the second derivative. And if I was to do the second derivative, I really would just go from this version of my derivative. I wouldn't use the quotient rule when I don't have to. The writing it as a fraction just helps me to figure out what critical values and critical numbers I have. So I take my second derivative, and that 2 is going to be gone, and then I'm going to have a positive 2/3 x to the -4/3. So of course, if I want, I can write that as 2 over 3x to the 4/3. There we go. And really that tells me that all I have to think about in my second derivative, because this was my first derivative sign chart, here is my second derivative sign chart. All I really have to think about is x being 0. We can see that the second derivative is not defined there either. So the concavity could only change on either side. So notice we're taking the cube root of something, raising it to the 4th power. So if I put in a negative number, I would have, the numerator of my second derivative is always positive. So if I put in a negative number, the denominator is going to be the cube root of a negative is negative, but raising it to the fourth is positive, so I have positive over positive, which is positive. So that tells me that we're going to be concave up. And then if I put in something that's greater than 0, like 5, positive over positive, so more positive. So in this case, concave up is going to be from negative infinity to infinity. Okay, so now we're ready to graph it. So you can put on your x-intercepts or x-intercept and y-intercept, and you can put on your local max and local min, or realize that 0, 0 is a local max and negative 1 is a local min, and then think about your concavity and see if you can put it all together and do the graph. Okay, so notice that we have our function that's increasing all the way up to 0, 0, and notice that we have, if you want, I can do my annotations in red. So notice that we have a function that's increasing up to 0, 0, and that's a local max, and then here's our 1, negative 1, so you can see right there that we have a local min. And so our function's increasing up to 0, 0, then it decreases down to 1, negative 1, and then it increases after that. Now, we don't have any place where the concavity changes, but notice that we are concave up here, even though it's a very slight concave up, but it's a concave up, and then we're concave up for the rest of the time. But at 0, 0, we have that cusp, and that's really something to recognize anytime you have that rational exponent, that's a fraction, because you can see that the function is continuous. There's no domain restrictions, but when you take a derivative, you do have a vertical asymptote at the derivative, and that's what's creating this idea right there. So that's where the cusp is coming from. But other than that, that is an example of a function with a rational exponent.